Beyond Zero Emissions Discussion Group. We would like to acknowledge that we're meeting on the land of the Kulin Nations and pay our respects to their elders, past and present. We'd also like to thank the University of Melbourne Energy Research Institute, our Zero Carbon Australia project partners, for this great venue. For those who haven't been to one of our discussion groups before, Beyond Zero Emissions is a very big group of volunteers researching and communicating ways that Australia's contributions to global warming can be reduced. Our goal is to transform Australia from a 19th century fossil fuel-based economy into a 21st century renewable-powered clean tech economy. Our projects include Zero Carbon Australia research, Repower Australia talks, media work, education programs, and much more. We're always looking for more volunteers to come and talk, so come and talk to us afterwards if you would like to get involved. We've recently had a bit of an overhaul of our volunteer acceptance program, so hopefully we can cope with volunteers better than we have in the past. This discussion group is a forum for climate change solutions, global warming solutions, with presentations by experts in their field, and is held on the first Monday of every month. Heat pump domestic hot water was a key recommendation of the Zero Carbon Australia Buildings Plan, which was released last year, to demonstrate how all existing buildings in Australia can reach zero emissions within 10 years. Richard Keech was a principal researcher of the Buildings Plan, and he's here this evening to explain how heat pumps work and answer the question that everyone has been asking: are heat pumps really better than solar hot water systems? Richard is an engineer working as an energy efficient consultant. He's also a regular contributor to Renew magazine, Renew Economy, and to the recently released Efficient Hot Water booklet published by the Australian Technology Association. We'd also like to welcome Dave Kerrin from Earthworker and Joe Cahill, Director at Everlast. They will tell you about their new Australian-made solar bolt-on heat pump. But first, here's Richard's presentation. Would you please welcome Richard?
Good evening, everybody. It's a pleasure to be here. Got a bit to get through. Let's get going. Okay, heat pumps. We'll talk about the application mechanism and implications of heat pumps. So what's a heat pump? Heat pumps are devices. Heat pumps are the mechanism that are at the heart of fridges, air conditioners, split system heaters, heat pump hot water systems, trigen plants, cryogenic systems. They're very widely used, and so what's the big deal about heat pumps? Why is a group like VZE talking about them? Well, heat pumps are really the only devices out there that harvest renewable ambient heat. And I'm going to come back to that term, so we'll talk about that in a minute. Heat pumps are really a key enabling technology for our modern civilization. Imagine a home or a supermarket without a fridge. If you had to ration your power, I bet you that the fridge would be one of the very last things that you would have to turn off. Imagine a large building in a hot climate without modern air conditioning. Imagine a vaccination program without refrigerated vaccines. So we have a lot to thank air conditioning and heat pumps for. And as they relate to VZE's story, heat pumps are a key enabler in moving away from fossil fuels, and in the context of the built environment, gas as a fuel in particular. So that's the electrification of homes that we've described in the VZE Buildings Plan. Coming back to this notion of renewable ambient heat, I think it's an important one. Everyone's familiar with renewable energy and has an idea what that means. Everyone's familiar with solar energy, wind power, etc. But probably most of you don't think of the heat in the environment around us, in the air, in the ground, in the water, as being a source of renewable energy. And in a really important way it is. Heat can be extracted from the air, the water, or the ground, And that's, in a very real sense, renewable. And we can use that. Heat is a low-grade form of energy as compared with electricity, which is a high-grade form of energy. And what that means is that joule for joule, electricity is energetically more valuable than heat. But often we only need heat. And before we launch into how heat pumps work, I need to establish a couple of foundation concepts. First is the difference between heat and temperature. In common everyday vernacular, heat and temperature are pretty much the same thing. But when we need to understand how heat pumps work, we need to distinguish between them in a more subtle way. Adding heat generally increases temperature. Heat, I tried to think of an analogy or a metaphor that explained this, and the best thing I could come up with is that heat energy is like heat energy is to matter what water is to a sponge. Imagine a wet sponge, the body of the sponge being the matter, and heat energy infused through it like water in a sponge. And if you have a dry sponge next to a wet sponge, the moisture will infuse from the wet. You'll follow a moisture gradient from the wettest to the driest, and they'll balance out. Just like a hot object touching a cold object will come to an equilibrium. The other point about this distinction is that adding a given amount of heat energy to two different objects can give rise to a different change in temperature because of the different properties of the material. Example is water and air have different. The property of the material that in physics is called the specific heat, and water, for example, has a high specific heat, so a given amount of heat will heat it less than that same amount of heat applied to air. Second foundation concept, coolth is a thing. It's not just some wonkish misuse of words. It really is a thing. Usable heat energy increases with the difference in temperature. So in absolute terms, there's energy embodied in material that has temperature, but in usable terms, it's temperature difference that matters. And that temperature difference can be a positive temperature difference or a negative temperature difference. It doesn't matter. So a hot object in a room has heat energy, but a cold object in a room arguably also has energy. So it's the magnitude of the temperature difference that matters. We're comfortable with this idea that a hot object has warmth. Likewise, a cold object has coolth. So a large block of ice embodies significant heat energy, even though it's cold. So adding coolth is extracting heat. So I want to do a compare and contrast. This diagram is meant to illustrate the conventional non-heat pump approach to how heat is often derived. We have some form of input energy. It might be wood, it might be gas, it might be electricity. It goes through some transformation, and that energy that goes in is directly turned into heat. And that's what I call a brute force approach, because if you pass electricity through a resistor to get heat, for example, like in a hairdryer, then that's taking a high-grade form of energy and turning it into heat directly and efficiently, arguably. But it's a waste of that high-grade energy because there are better ways of doing it. So that's the bad way. That's just taking the input energy and transforming it directly into heat. A heat pump does it better. It takes, in this example we've got some input energy, 10 megajoules for illustration, and our mechanism is able to take 20 megajoules of ambient heat. That's heat embodied in the ambient environment, and together those energies combine to give some delivered heat. Now, there's still going to be losses in the system, but the point is that the applied energy through a clever mechanism is able to leverage heat energy that's in the ambient environment, and that's the essence of a heat pump. And there are many physical principles that can do that sort of thing. the conventional refrigerator involves what's called the Vapour Compression cycle. I'll come back to that. But there are other things. Absorption chillers you may have heard of, thermoelectric cooling, magnetic cooling, thermoacoustic cooling. They're just different physical principles that can all, in one way or another, move heat. Time doesn't allow us to look at all of these in detail. But I will just give a very, very quick history. Use of heat pumps first demonstrated way back in the late 18th century. Scotsman, William Cullen. The first demonstration of a vapour compression heat pump wasn't a practical device, but the demonstration was early mid-19th century. And Harrison, which, interesting quirk, Mr. Harrison was actually from Geelong. Well, he's an Englishman, but the first practical vapour compression heat pump actually happened here in Victoria. First gas absorption heat pump later on, but it wasn't until about 100 years ago that the first recognisably modern type of refrigerator first came on the scene. So they've been a long time in development, and for a lot of their history they've just been things that we think of as fridges. Quickly I want to touch on absorption heat pumps, but not in much depth. Basically there's a three-stage process: evaporation, absorption, and regeneration of usually a gas and liquid mixture like water and ammonia. The point about absorption heat pumps is that they take a form of heat and let us generate some coolth out of that process. It's not that efficient generally, but absorption heat pump systems are useful where you've got some waste form of heat. Trigeneration is an example. I won't explain it if you don't know what that is, but trigen plants are an example where waste heat is utilised to create useful cool. Here's an example of an old, early 20th century gas-powered refrigerator that used absorption chilling technology. Maybe your grandma had one. Okay, jump forward 100 years and we've got a more conventional, recognisable split system heat pump. This is, I think, the quintessential modern heat pump arrangement. And let's look at what's going on there. As a schematic, we've got a circuit. We've got a gas or fluid passing around a circuit. At the top, you see a compressor pushing it through the circuit, expansion valve at the bottom. So we've got, in this example, we've got a reservoir of heat on the left. This pertains to heating mode of a heat pump. So we're taking heat out of the air in this case and sending it to a sink. So this term is reservoir or source, is where the heat's coming from, and the sink is where we're sending the heat to. Now, to explain this properly, there's a couple of basic principles that we need to understand. Firstly, and quite obviously, heat flows from hot to cold. Heat flows down the temperature gradient is how physicists look at it. The steeper the slope, the faster the flow. So, that's intuitively understood that if you've got a steep slope, you go faster. In this case, the steepness of the slope represents the change in temperature involved. And the faster the flow is actually the thermal power, how quickly the energy is flowing. So an example here, winter scenario, outside a wall, it's 10 degrees, inside the house it's 20 degrees. So you've got a temperature slope or profile across that wall. And that leads to heat flowing from right to left. But the same arrangement could be gas in a pipe, in the pipe wall and inside the home. We've got gas flowing, heat energy flowing from right to left. Second basic principle, pressurizing a gas raises the temperature. So this is where things start to get interesting. There's this notion that physicists call adiabatic heating. This is really important, that adding heat energy isn't the only way something can get hot. Something can get hot, or a gas can get hot by squeezing it. You may have taken a bike pump and squeezed it and felt the nozzle get very hot. In this case, in thermodynamic terms, work is done that the entropy doesn't change if it's done ideally, and it's a reversible process. Adiabatic heating and cooling are the reason, for example, why it's cooler in the upper atmosphere than it is in the lower atmosphere, even though hot air rises. So that might be counterintuitive. You might think if hot air rises, it should be hotter up top, but no, it's because as air rises, the temperature, the pressure reduces, and because the pressure reduces, it gets cooler. So back to our pipe example, if we've squeezed the gas in the pipe and the temperature's gone from 10 to 30, then voila, we have reversed the temperature gradient. And instead of flowing from right to left, the heat's now going to flow from left to right. So that's the essence of a heat pump, is that we do a bit of a trick to almost get the heat to flow uphill by jacking it up and getting the temperature to increase, even though we're not really adding a lot of heat. So back to, as it relates back to this diagram, to the right-hand side of the compressor is going to be high pressure all the way around, and that expansion valve is simply what it says. It's just like a little hole, regulated size, that as the high pressure gas passes through it, it drops pressure through there, and so on the left-hand side you've got low pressure. But we can split that another way, where the top part of all this is the high heat part and the bottom half is the low heat part. So that explanation is sufficient to see how heat is moving, in this example, out of colder air on the left and into a house that's already warmer than the outside on the right. But there's another element that I haven't touched on yet, and that's this idea of phase change. I mean, everyone, I hope, is comfortable with this idea that moving from a gas to a liquid involves a phase change. And phase change is important in a heat pump because lots of heat energy, we can get a lot of heat energy from a small change in temperature. And that fact makes heat pumps more efficient if we can utilise phase change. So latent heat is released on condensation, for example, or latent heat is absorbed when you evaporate. And that's something that makes heat pumps much more efficient. So as it relates to our example, on the left, we absorb heat from the environment and liquid evaporates into a gas, and on the right the gas condenses into a liquid as the heat is given off. So generically we term the heat exchanger device on the left the evaporator and the one on the right the condenser, because of the functions they serve. But they switch around in the reverse cycle arrangement. So reverse cycle, literally the pump goes backwards, the heat exchanger that serves as the evaporator becomes the condenser, and vice versa. In the example we saw the ambient outside air being serving as the source or the reservoir of heat, but air and ground and water can all serve as reservoirs of heat. Another commonly used form of heat pump involves the use of the ground as the source of the heat. These are called ground source heat pumps, sometimes known as geothermal heat pumps, not to be confused with devices that actually use very hot ground, deep down ground heat. These just use the natural year-round stable ground temperature in the order of 5 to 50 metres deep. Now, ground source heat pumps are more expensive because you've got to drill and dig, and there's a lot more capital cost. And the trade-off is that generally they're more efficient because of that year-round stable temperature. They're quieter outside because they generally don't use a fan-forced arrangement to get the heat out of the heat source. So there's no external fan. So just quickly jump to this arrangement. Broadly, you can have horizontal loops, vertical loops, diagonal loops. There's different ways of putting pipes in the ground that serve as a way of coupling our fluid or gas with the ground to get heat in or out. I want to quickly just compare and contrast heat pump style cooling with evaporative cooling. Everyone's familiar with the old-fashioned evaporative cooler, and likewise everyone's familiar with a conventional air conditioner that uses a heat pump. Evaporative air conditioners work by increasing humidity. There's evaporation that goes on, that absorbs heat, lowers the temperature, increases the humidity. Depending on how high that humidity gets, that's not necessarily a good thing for comfort. The other point about evaporative air conditioners is that they're generally one pass. In other words, the air comes in, gets cooled a bit, and then passes straight out again. Whereas heat pump type cooling, reverse cycle, refrigerative air conditioners typically are able to recirculate air and keep it cool within a room. There's limited temperature drop achievable with evaporative air conditioners. So if it's 40 degrees outside and you can only get a 15 degree, or say a 10 degree temperature drop, then you're still not going to be comfortable, especially when it's humid. And the other point is that they tend to have continuous requirement for water, unlike a heat pump. So, and there's no reverse cycle equivalent with an evaporative cooler. They can only be used for cooling. So, as a result of those factors, I'm generally a big fan of heat pumps instead of evaporative systems. Just to quickly talk about performance of heat pumps. Just to define some terms, if we talk, say W is our applied energy, QC is the heat we extract from our reservoir, and we introduce the term coefficient of performance to represent how well we deliver heating, and energy efficiency ratio is the term generally given to the same thing for a cooler. So just quickly, the difference between the COP, or coefficient of performance, versus the EER. Here, the blue box represents our system. We've got heat, work going in from the left. That's the electrical energy, the heat coming from the environment at the top, and this QC plus W represents what we get out of the end result. So COP is the ratio of what you put into what you get out, QC plus W on W. Compare that with the cooling case, where the reservoir is actually the inside of the house, and what you're ejecting out into the outside is the QC plus W. So the ratio is slightly different. It's the QC on W is how you measure the performance of a cooler. So from strictly thermodynamic terms, coefficient of performance isn't the same as efficiency. But for practical discussions, it's useful for treating coefficient of performance as if it were an efficiency. Okay, I think we're running out of time, so I might not give this the attention it deserves, but just say that for a given system, COP isn't the value. If we say that a heat pump has a certain coefficient of performance, that's a coefficient of performance measured under certain conditions, and we can't say that coefficient of performance is achieved all the time. It varies considerably with the outside temperature and the inside temperature. So, for example, if all these rows relate to the same system, the same operating with the same device. If the worst case situation, you might have a really cold outside, and in this example we're trying to heat in every case. A cold reservoir, we're trying to deliver heat into something that's already very hot, you're probably going to get a bad coefficient of performance. But you're adding heat into a swimming pool and it's already very hot outside, that same system is going to give you a tremendously good coefficient of performance. And likewise, in the intermediate cases, the coefficient of performance will vary. In terms of domestic air conditioners and ones that can also serve as heaters, the best source of information about what's out there is energyrating.gov.au, the government's equipment energy efficiency program. And here's an excerpt that I looked at yesterday. Best on the market. This is sorted by cooling. The actual page on the website continues off to the right and looks at heating, but just to make it readable, I've just stopped it there. Best on the market is a Dakin unit, rated at 7 stars, and you can see on the top row the input power and the output power. The output power is thermal power, not electrical power. And the ratio of the 2.5 to the 0.42 you can think of as the coefficient of performance. And in that case, that's about 5.9 or 6. Okay? So in other words, you deliver 0.42 kilowatts with electrical input and you're getting out 2.5 kilowatts of thermal output delivered into your home. And that ratio is what we consider the coefficient of performance. And that's a particularly good example. That's the best on the market at the moment. Running out of time, I wanted to quickly talk about refrigerants. Different classes, most of them use phase change. They don't all. Some of them are using the absorption systems. There's a whole bunch of considerations about the materials we use as refrigerants. I won't go into those because we're running out of time. Older refrigerants like Freon had a high ozone depleting potential, high global warming potential. They're largely gone now. In common use at the moment, we've got hydrofluorocarbons that are still allowed but are increasingly being regulated out of existence. A common one is, for example, tetrafluoroethane, which better known as 134A. It's probably the refrigerant in Dave's system when he talks about it. Or so-called natural refrigerants are becoming more common. These are more common hydrocarbons like butane, and butane is known as R600. There are other gases out there that are used as refrigerants. Air is a refrigerant, or just plain old air can be used as a refrigerant. Water vapour can be used as a refrigerant. CO2 is increasingly used as a refrigerant. So, actually I'll skip that. Okay, quickly wanted to talk about, actually I'm running out of time, I think I'll skip that as well. A lot of what we've just been talking about applies to heat pumps. Generally, using air conditioners as a specific case. but did want to spend a bit of time talking about heat pumps used as systems to heat hot water. Heat pumps earn, in Australia by government regulation, heat pumps earn renewable energy credits called STCs. The better they perform, the more credits they get and the more rebate you get on buying them. Heat pump hot water services tend to be more expensive, but it's a trade-off between capital cost and running cost. They will more than pay for themselves in reduced running costs, especially with energy costs increasing. They're a similar price and their performance in rough terms to solar hot water services, but they're generally easier to install. They have fewer contingent issues than solar systems. For example, you don't have to worry so much about whether your solar panel might be shaded, or you don't have to worry about the frost protection on a solar panel that you would with a solar hot water service. But over and above those things, this is one of the conclusions from the BZE Buildings Plan, was that one of the main reasons why heat pump hot water services are better than solar hot water services is that across the course of a year, not only do they use slightly less energy in a similar application, but they're much easier on the grid. So you can see the blue line representing solar. In the summer months, they're far and away better than the heat pump. But in the winter months, the conventional electric boosted solar is using a lot more power. Especially because with our electricity grid, it's likely that peak requirements are going to move from summer to winter. It's important to try and get this wintertime energy use down. And so the fact that the heat pump, while it's still using more energy in winter than in summer, is much less peaky. That potentially has good implications for the widespread use of heat pumps for hot water services when applied en masse. So, quickly, some tips from my own experience about deploying heat pumps for yourself. Avoid ducted systems. Compare performance using that site I showed you before, energyrating.gov.au. Take care with pipe insulation. Over-specify it. It's invariably something that shortcuts are taken in common practice. There can be noise issues. Be careful where you put them. You stick them outside a bedroom window for winter on a winter night. You might not be making friends. Check how noisy they are. Some systems are quieter than others. Choose one with a low global warming potential if you can, because when they leak, you don't want that to have a bad emissive effect. Allow for unimpeded airflow. The outside part of a heat pump needs to be able to exchange heat with the ambient air relatively unimpeded. I've seen some pretty bad examples of air cons squeezed into really tight spots or right next to another one in ways that are going to lead to bad performance. Use a qualified installer. Okay, here are a couple of quick examples from my own experience of things done badly. Here we've got the flow and return line for refrigerants in the same sheet, and because the outbound and the inbound flow of refrigerant are at different temperatures, you're going to be losing so much heat that would be almost ineffective. This was on a roof of a site that I visited a couple of months ago. I'm not quite sure what caused that insulation to degrade. I suspect it was birds, but it's really badly degraded. Often these systems get installed in places that don't get inspected very often. They're out of sight, out of mind, and these were in use at the time that I took this photo, and you can just see the shininess on the pipes. That's the condensation on the pipes. Glistening is showing how inefficient it is. Major loss of heat. Incomplete insulation. This is actually on my own house. Straight after it was installed, that's how the installer left it. With this is at the bottom of the page. It's just going into the house, into the indoor unit of the house, just behind the wall. So they left the last bit uninsulated, but worse, at the bottom the pipes were touching. Not as bad as the earlier one where they're touching almost for the whole length, but touching copper to copper is a very good conductor. So that's what that's my remedy. And by the way, that's not what you see when you go to my place. It is covered. You don't see it. Okay, to finish off, back to our idea of a heat pump being able to leverage that ambient heat in the environment. That aligns well, I think, with my favourite definition of sustainability, which comes from Paul Hawkins. That sustainability is aligning with natural forces, or at least not defying them. And I think this idea that we can cleverly and elegantly take a high-grade energy like electricity and use it to pull ambient heat out of the air to deliver heat for our comfort. I think that's a great example. Thank you very much. Any questions? Do we have time for questions? Or do we want to take questions at the end? Okay, we'll take questions at the end. Okay? There's a little heat pump. We're sort of for amigos, basically. So I guess my role was to explain, I suppose, the non-technical, infrastructure for earthwork. Because no matter how technologically advanced we get, you can see from the experience, especially of small manufacturers, everyone's running into trouble. If we're just left to the private market, and that's all we've got, because it will be cheaper to manufacture in China and elsewhere in the depressed labour economies. So Earthworker Cooperative was a conversation that started 16 years ago in the organised labour movement. Lots of furious debate, because it was a massive step outside of the square for unions to be looking at supporting the setting up of cooperatives, and especially if you think back to 16 years ago, there were a lot of changes afoot, and over the intervening 16 years, a lot of changes generally as to how unions can legally function. In fact, legally, they can't do much anymore. Certainly in an agreement, it is illegal to preference locally made goods. So we can't put that into a union in our own country. So the discussion was around how do we reintroduce manufacturing of the renewable technologies so that we can, I suppose, to some extent at least, without putting rose-coloured glasses on, turn crisis into opportunity. Literally work our way out of climate emergency. Provide at least one mainstay within the question of drawing carbon down out of the atmosphere that did not rely on a service sector economy. Certainly, union side, we see it every day. We're at 80% service sector economy. You would all know that. Greece was at 60% before its collapse. So if we want to put a green tinge around our service sector economy, maybe even take it into the 90th percentile by importing all of the green goods that we need as a nation, then we tie our strategy to draw carbon down out of the atmosphere to a service sector economy, and I would argue that's built on sand. We're not going to have a lot of choice, but where we do have choice, we need to start putting the manufacturing component back in, so we have the full productive cycle: manufacture, installation and maintenance.
In fact, it was the national president of the miners' union, Tony Mayer, who said, we can either do this the hard way or the harder way. And he said, we need to choose the harder way. I agree with Tony on that. So how were we going to do it? Well, we started a discussion. People like Joe and I came from opposite sides of the political and industrial fence. As Joe says in one of the videos, we're on opposite sides of the picket. But we began a discussion with Everlast around what assets did we actually share? What as employers and organised labour, what were the things we did every day of the week that could perhaps, if looked at in another way, be used for the common good? The obvious one was the agreement. So the agreement that employers and unions negotiate, we looked at the wages component of that. Was there a chance to, in the wage increase, make solid goods that are made here available to ordinary working people and their families? Well, yes, there was. So we're cutting a very long story short here because of your time constraints, but we're in now four of those agreements, university agreements, the largest Shire Council in Victoria, we're in that agreement. We're in a community services agreement where there are 500 workers employed. So we're just on the cusp now of pushing that out there. A week ago, we ran a fortnight-long crowdfunding campaign done by the younger earth workers who, by the way, are taking earth worker over. They're absolutely brilliant. 2 weeks, 78.5 grand. People donated 78.5 grand. Just ordinary people, a lot of them young, student workers, just love the project and want it to work. So it was very, very uplifting. That's now putting us in the position where we can at least begin the process of Everlast coming over into the Reapers Future Workers Cooperative. The next stage is raising the capital, hopefully from workers' capital, to cover a dead period, a non-productive period where Dandenong factory moves to Morwell. And at that point, of course, there's a lot of not just practical work, but a lot of really good, solid politics that unites a wide spectrum politically of people that we want to do. Because with a viable factory in Morwell, we've always said we want to stamp that template out into every state and territory of Australia, using the enterprise agreements that employers and unions negotiate on a regular basis as one of the main means to distribute or sell the goods. Not-for-profit manufacturing hasn't been done before in this country, to our knowledge, not on any scale at least, is where we're resting the ownership. So worker owners in not-for-profit manufacturing cooperatives. An Indigenous intake into every worker owner intake, women into the trades. We want to be and get our political correctness correct. For us, that just means being good. So we have a plan. We want to get then into the full range of the renewable technologies, especially solar thermal, large, medium, and small wind. We believe we can do it in this country. There was certainly, a dozen years ago, 10 of the Largaway generators. Some of you might know about that were done in Latrobe Valley. The Danes came out to inspect those generators and said they were world's best practice. So we know we've got the skill base. But that skill base is running out in Latrobe Valley. Average age in the mining industry now, where a lot of that engineering goes on, is 55. Well, in fact, it's above 55 now. So we will that skill base will be decimated if the current government especially continues down the path it's going. So we've got to create something practical where the hammer strikes. Something practical that works, that can provide some hope for people in dealing with climate emergency and jobs. So we've run the idea that we will work our way out of climate emergency. One arm of all of the myriad of ways we're dealing with climate emergency will be a manufacturing component. And so we're getting closer and closer. Now we're in production at least with the partnership. It's not perfect. And we're running into problems, but we're alive and kicking and developing and growing. So I guess that's the sort of the organisation structural side of it. And at the moment, I guess one word would sum it up is transformation. We're transforming in a whole number of ways. The process of Everlast transforming over into the co-op, a great little Australian company that's actually going to be mutualised. We're transforming inside Earthworker, that younger generation coming through. A lot of them have been locking on to coal machinery and so forth for some years, and still going to do it, and good luck to them, but they want a positive alternative. They're desperate for it. And so there's a whole bunch of talent coming in now and taking over from old-timers like me. So it's a hopeful message. Very rare in Australia to see the level of cooperation. Russell North, the National Party member from Morwell, loves us. And in fact, we're told, because we went in, without talking out of school, and I won't go into detail, but we went and had a meeting about some procurement. And anyway, Russell's saying that he's going to make an announcement. I don't know what that will be, but I'll settle for any announcement that someone says positive. So yeah, look, there's a lot of support across a wide spectrum. Certainly within the Labor Party, a lot of support. The Greens goes without saying. So, you know, yeah, it's a hopeful message, and I know for me personally, my time of life, because I've been there for the 16 years of this, it just feels so right. You know, I mean, I've stood in the way of a lot of trucks on picket lines, and this is something really, really constructive that's putting in place a new vision for all of us. So, thanks. So I'll introduce Joe. From Everlast, who's the CEO at Everlast.
Hi guys, I've been in manufacturing for well over 30 years, starting in the early 80s with a company you might know, which is an icon in Australia, BTR Nilex. It doesn't exist anymore. Employed Australia-wide around about 18,000 people. All those jobs are gone. I've seen hundreds of thousands of jobs disappear in that 30 years. When I first started in manufacturing, we had a manufacturing sector that was about 42%. Now it's less than 18%. So when Dave came knocking on the door, I was a little bit hesitant, a little bit reluctant, because, you know, we've had big fair stoushes with the unions over those years. Some good, some bad. But when he came and sat down, we had a discussion with a partner of mine who's now deceased, Bob Higginson. You know, what he was saying to us made sense. You know, the realisation is that, you know, imported goods are cheaper. There's been many Australian-made campaigns that haven't worked. Why haven't they worked? It's because the supermarket chains don't want it to work. They will tap you on the shoulder and say, we're not going to list your line anymore. So there's another, you know, lots and lots of jobs just disappear just by a tap on the shoulder. You know, they want their own brands, their sub-brands, and their cheap brands all to be controlled by them. So there's not a lot of opportunity anymore. So what we're looking at in a non-for-profit cooperative is the chance to compete against imported goods. Over the years, we've come up against quoting with imported goods a number of times, and the general difference is the profit that we have to make to be competitive. So yeah, we can supply at a cost basis to be competitive, but shareholders don't want that. You know, they want to see profits. People who are investing in manufacturing want to see profits. So if we can take that profit out of the company and use the jobs as profit, well then all of a sudden we can compete again. So it made a lot of sense. Also, you know, we're addressing climate change, which is a really, really important issue. So we sat down, the discussion started, and slowly we developed a formula, you know, to bring this all into fruition. So what we do at Everlast, we've been making high quality marine grade stainless steel tanks for domestic, commercial and solar hot water now for about 17 years. It's the only tank on the market that's fully corrosion resistant because of its outer polymer case. The polymer case is 30% recyclable plastics, and the whole case is recyclable. So it's a great product. It's got a 15-year warranty, and if you have a look at the terms of investment of a heat pump and a stainless steel tank, and look at the savings over the lifetime of the product, well then, you know, you've got an investment of fully installed somewhere just less than $3,000, but that return over the lifetime of the product is above, in excess of $25,000 for the normal household. So in terms of investment, you wouldn't get a better investment. So if I said to you, you know, give me $3,000 and in 15 years I'm going to give you $25,000, you'd be throwing as many dollars at me as you possibly could. It's better than superannuation, way better than fixed deposits. So, you know, everybody understands dollars and cents, and that's the message we're trying to get out. A high-grade product, fantastic warranty period, a full factory warranty, a fantastic return on investment. So there's not much to like about it, and we're also addressing climate change. And hopefully we're going to put some more skilled jobs down into those areas of poor eco and socio-economics and build a future for the youth. And you know, that's going to start in Morwell in the Latrobe Valley, who's very dependent on coal, as you all know. We're not too sure how long those jobs are going to be available down there because of the infrastructure and the money you have to spend on the upkeep of that. So, you know, it's all in a good cause, and it brings unionists, you know, business owners, politicians on either side of the bench, all together, united on a very great initiative. So, you know, we ask you to spread the word and let people know what we're doing, because it's a win-win for everybody. And the most important thing is it's a win for the youth of Australia and a win for climate change for Australia. And that's what we should all be considering. It's not our generation, maybe not the generation after us, but certainly the generation after them. Because there'll be nothing left, there'll be no jobs. There'll be, you know, Australia will be arid. You know, we'll all be living in the tropics. Most of it will be desert, and that's real, and that's what we have to address. I'll pass you on to Chris, and he can tell you all about the bulk and heat pump.
Okay, I think the merits of manufacturing, you know, have been well covered there. I guess the only thing I will say is that the name Siddons goes back to my grandfather in World War II, with the Citroen Spanners. You can have a man who grabbed a spanner, I think you know that. I cut my early management teeth in the company Ramsay Fasteners, which was a manufacturing business, and also in waffle insulation manufacturing, which we were involved in for a number of years when insulating houses was quite a radical idea back in the 70s. So I have some affinity with this whole thing with manufacturing, what Dave's been talking about. So the whole idea of being green is something my father was really passionate about in the 70s, and John Siddons. So it's kind of rubbed off on me. So if we can make a business out of doing green things, I think that makes a lot of sense. Now the great thing about a heat pump, and I know there's been a lot of things that talk about heat pumps today, but the really good thing about it, and where I'm passionate about it, is that we have a situation with the electrical grid, the power grid, with demands coming off the grid and other inputs to the grid like PV, like wind, causing the grid to fluctuate around. So in comes smart meters, so the authorities can kind of work out how to regulate the grid and balance it out and get rid of the peaks. Now the heat pump is an ideal appliance to do that. Absolutely ideal, because it only needs to run for about 3 hours a day in 24. It doesn't care really which 24 you choose, but which 3 hours from the 24 you choose, but 3 hours is about all it needs. So if there were a whole lot of heat pump water heaters out there and connected to the grid, it would be fantastic if there was a switching device like the smart meters, so that somebody can sit in the control room and say, right, peak demand, throw out all the heat pumps. No one wouldn't even know it, because the heat pump's working on a storage tank, which effectively is like a battery unit to store energy. So it really doesn't matter if you chuck the heat pumps off for a little while and bring them back on later. So I would argue firstly that some of the things that happen in Australia, like building developments on a reticulated gas system, are not allowed, our heat pumps are not allowed here because there's gas. You've got to have something that's gas powered. So what it does, it holds our heat pumps and technologies that play to that whole idea, like PV and all these kind of things which are coming. It makes it difficult to get these technologies in when you ban them straight up by saying, well, you can't have it because we've got a gas grid here. Yeah, but we've also got a power grid, and it needs a bit of assistance also. I would argue the power grid needs are probably greater than the needs of the gas grid, and all the gas is being sold overseas anyway. So what's the big issue about that? I don't kind of get that. But the other thing is we've got a new government that's about to repeal the carbon tax, I believe, this week. And they're going to put in an agenda of direct action. Now, I would say the single easiest, one of the single easiest things you could do is to make it attractive for people to buy one of these bolt-ons, attach it to an electric element water heater, and save power, because they only cost about $200 a year to run. That's all. And I'll save 3/4 of the power you would otherwise consume with an electric element water heater. And there's probably about, what, 2 million or something? There's a lot of them out there. So if you're able to buy one of those and get some kind of a rebate for it to connect it to an electric element water heater, straight away you save a whole lot of carbon emission, easily done. But we have a system at the moment that says we can't get a rebate for a heat pump water heater unless we sell it with a brand new storage tank, even though the one that's in there might have a life of 10 or 15 years. Now, that doesn't kind of make sense from the point of view of sustainability, not the way I think about it. So if you're going to have rebates, why don't you have a rebate for that connected to an existing storage tank, as well as have a rebate for that connected to a brand new storage tank? You shouldn't have to rip out a 2-year-old storage tank to put that in with a new one to get a rebate. It doesn't make sense if we're serious about sustainability. So that's probably some of the things I would say, just on the legal front. But the other thing about the technology, another thing that's great about heat pumps, when it's heating the water, it's throwing out cold air. So it's really easy to get some kind of cogeneration kind of ideas working. A really simple one would be to capture the cold air that's running out of the top of that and throw it back into the kitchen or the bedroom of a domestic dwelling. You know, particularly in southern climates where really you don't need air conditioning that much. If they're well insulated and well built, probably the air conditioning effect of that for the 3 hours it needs to run in the afternoon would get up. Throw that cold air in, and because the air that's going out the top of that is about 8 degrees cooler than the air that's being sucked into it. So if it's 33 degrees outside, that's 25 degrees going in. So you can capture that quite easily. So these are some of the things we've talked about. And maybe, you know, as we go forward and try and get this, you know, cooperative thing going, you know, some of these kind of add-on ideas or being able to use, you know, things in smart ways might make sense. The other thing would be if you could take heat sources, such as the heat that's generated by your refrigerator, and feed it into the evaporator or where the air is sucking into the heat pump, you're going to make it run more efficiently and your fridge as well. A 10-degree rise in the ambient air will deliver a 20% improvement in the runtime of the heat pump. So there's some really simple things to do there, just with simple design. And you know, that's why I feel when I made comments before, if we could get some of these constraints out of the way and allow heat pumps to sort of, you know, give them a fair go, I think a lot of these technologies could come forward, and cogenerations, a lot of ideas you can do with heat pumps, with TVs, panels and all of that. There's a lot that can be done. So that's really all I wanted to say about heat pumps.
Yeah, questions?
Where are the people who are working on dealing with those other problems, do you know? And why don't you know? It seems to me that the things that are keeping this technology from growing more in the market needs to be dealt with on a political level.
Well, it's a kind of a chicken and the egg issue, I think, you know, for us to be able to employ more engineers and people in R&D and the like to develop some of these things. For instance, gas, there'll be refrigerant that's in there. We did some work a few years back on R290, which is a hydrocarbon gas. And it's a very good refrigerant. That's essentially propane. And there's other gases and refrigerants as well. That's just one little thing that comes to mind. But look, I suppose the thing here is that you need scale. You know, you need size and you need volumes. And It's probably one of the problems that we have in this country, that we can't get the volumes or the scale. So what we tend to do is we team up with others in the world. And so what we've done with our heat pump, we've got a partner in China, I have to say, but we have got a partner in China. We work with them, and they've got a big organisation, so we sort of swap ideas and we tell them things and they tell us things, and we sort of work collaboratively. We'd like to see more of the value add and the technical side of it, the R&D, back here in Australia. It is a function of economics, and I guess what's been
I'm really talking about the non-technical things.
I think one of the problems we've got is when our governments privatised our energy resources, there was targets and penalties put into that privatisation. So, if they don't reach certain sales targets, well, then there's, penalties on our governments. Same as with free trade agreements. And so the governments, aren't really interested in pushing renewables. Only in the areas where their infrastructure doesn't reach. And then they're all for it, because it's, it's saving them money. But in the general rule is those sales targets and those penalties stop our governments from pushing into mainstream renewable energies. I think that's the whole problem. And it's not only with energy, it's transportation and all those things that they've privatised. So it comes back and bites them on the bum, because then you can't go forward. And really we're in the hands of the multinationals who dictate to our governments what we can and what we can't do through stupid free trade agreements. How stupid is it that our government can't buy Holden cars to save 12,000 employees? And I'm saying that if Holden was a not-for-profit cooperative, they'd be selling Commodores for $25,000. So it generates a whole demand for them. But they're not interested in that, because that's not conducive to their mainstream agendas.
Over here.
Look, my name is Tony. I already know that, and one of the next year I've got one of the tanks already installed in my house. And also disagree with you a little bit. There are locally made products which people don't understand, and even the builders don't know that. Even the plumbers and the electricians don't even know that. So I did a lot of research trying to find this product. With various valves to conserve energy, and putting panels up which are locally made, putting double glazed windows which are locally made, and putting skylights which are locally made, and insulated doors, all those things. So there is things there, but the knowledge within the industry is really absolutely crap, basically. Even when you're trying to talk energy efficiency to a plumber, he doesn't understand, right? Or an electrician. So I was going up there all the time, but nevertheless I ended up with a 7.5 star house, right? But I didn't know that they had come then, because otherwise I would have definitely gone on that. And also knew John Siddons pretty well. And I can't remember whether you know me or not, because I'm Tony days, but that's quite a few years ago, maybe 20 years ago almost now. Yeah. But I spoke to John when he was working on the wave things in Western Australia. So all the force good, guys. And it's the only way. The reason why I'm here is because I've got 7 grandkids, and it's their future. And it's so serious because every time a manufacturer goes broke, we're losing jobs and losing part of the future.
Thanks. I think the next question was over here, and then Carol.
How big is the unit? What are the dimensions like?
Dimension?
Yeah, on the
bolt-on.
Of the bolt-on? Of the bolt-on?
Yeah, bolt-on.
So you know what a 600 by 600 slab looks like?
Yeah.
Yeah, basically if you put one of those down on the ground and set it, it would sit very neatly on a 600 by 600 slab, and it would probably be about that high. It's about 500.
Okay, so you could actually put it in the roof space if you had a big...
Okay, you could put it in a roof space, and you get the heat from the roof, and that would make it run really fast. Like we've tested it between -5 and 45. At 45 degrees heat, live. So yeah, 45 degree heat is good. Trouble is up on the roof space, you've got a lot of dust, and if you stick it up there and forget it, if you put dust or you gum up the evaporator coils, and you can't get the airflow coming through, it's going to lose its efficiency. So it's very dependent on airflow. A heat pump's not looking for sunshine, it's looking for airflow. Warm air and humid air is what it's looking for. It doesn't need to be sunshine, but that's what it wants. And it needs that flow through the evaporator coil, and that's where it gets the heat transfer. So roof space is okay. What I would say with a roof space, you'd be better off with it, is put the heat pump down on that 600 by 600 slab, and maybe have some kind of fan that you hook up in parallel. Take some of that really hot heat, because sometimes it gets to like 60 degrees up there. You can get like a furnace up there, and that's not good for the heat pump. So maybe get some of that heat and push it down and push it into the path of the evaporator. That would be something you could possibly do.
We've got to, hopefully going to get to manufacture this little solar ventilator. Just within minutes it'll take your roof cavity down to 28 degrees, and it'll be wonderful to be able to use that heat.
Carol.
I wonder whether you've done any work on a replacement for gas-fired hydronic heating.
We can do that. It's just a matter of putting an internal coil inside the tank. So it'll run on a completely separate system. So what will happen is your wetback system off your either Canara heater or wood-fired burner, the water will circulate through a heat exchanger on the back of that, go through a coil in the tank, which then the energy will dissipate out of that coil and put heat into the water. So it's a very, very efficient way of boosting hot water. And we're actually looking at developing a complete system at the moment to offer for that. It's also a good application for hydronic heating. Hydronic heating is very, very small in this country, but it's a fantastic way of heating. It's very, very passive, so people with allergies and stuff like that, you don't have dust blowing all around the room. And we're looking at developing a complete system for that as well. And even if it's just for a bathroom reno or something like that, where you can have hydronic towel racks and heating the bathroom floor, it's very effective, and it'll all be an all-in-one unit.
And can I just add a comment to that as well? So Joe mentioned wetbacks there, so we're actually doing a little bit of work on adding a heat pump and also the evacuated tube to the wetback. So if you have a wetback, you've got evacuated tube when the sun does shine, and you've got a heat pump when the sun doesn't shine. You've got all those technologies pushing heat into it. Well, that's not a bad way to get some serious heat into the storage tank. So you can then use it for hydronic. That would be a very simple way to create a heat source for a hydronic system.
Yeah, okay.
There's some sort of size restriction on the tanks, and there's they need a large tank and normally just better stored energy and stuff. We need it carry on off somewhere.
Depends on the amount of water usage in the household. Basically what you're doing is the heat pump comes on and it'll bring that full tank to storage. So if there's only 2 people, say living in a unit or something like that, the 160 litre tank would be more than ample. Say 3 or 4 people, 250 litre, and above that is 315 litre. One of the good things about the Everlast tank, it's got the best heat loss of any storage tank on the market. So what you put in there stays in there for longer.
Can I add a point about that as well? Oh, no, don't worry. Yeah, up the back. Yeah.
Just so exactly on that point about heat loss, I'm off grid now and trying to store PV energy in the hot water tank, but kind of going nowhere because within 24 hours it's already in the grid again. So I guess just on that comment about that tank being on the grid, what is it that achieves that performance, and where is it in terms of general tanks?
Well, there's two different kinds of tanks really. There's the gas storage tank, which is really instantaneous, a little bit better than instantaneous. They've got very, very small storage capacities, generally 90 litres or 110 litres. But once you deplete that, when the gas burner comes on, they can replenish that very, very quickly. So the requirement for heat loss isn't stringent. In fact, I don't even know if they have maps on gas storage tanks. I'm pretty sure they don't.
No, I don't think they do.
But on electric storage tanks, where most of the energy comes from off-peak, which is after 1 a.m., well then they're very, very stringent on the insulation properties. This tank here has got around about 65 millimetres of closed cell insulation all around it. And what they do is, part of the watermark testing is you have to have heat loss tested, which is under MEX.
Is that the 2 kilowatt hours a day?
Yeah, exactly.
So I know, so we've got an Edwards solar hot water tank, so it'd be similar to the kind of solar tanks with the electric booster that people have all over the place.
Is it on the roof one or?
It's on the roof.
Yeah. Okay.
So yeah, it's in a cold environment.
Yeah.
And so it's hard to know at the moment. It's got a glycol loop going through it as well, so I don't know whether the heat's been lost.
Transfer through
You've
that.
got 2 more pipes coming in and out, and the heat fluid.
As far as heat loss goes, the closed systems on the roof aren't really good because of the high fluctuations in temperature because of that glycol component.
Yeah, so
Where the split systems are highly efficient when it comes to heat loss.
So generally, so even the connection with a standard tank like that, where you've got pipes just standard cold water in and hot water out, those pipe connections aren't adding significant bit of the loss. Like the limitation is just the...
No, the biggest heat loss on our tank is actually through the PTR because it's a large field that can transfer heat very, very quickly. So we recommend that there are special insulation woods for those PTR valves.
Valve Cozy, they're called.
Sorry?
There's a brand called Valve Cozy, which is the only one I'm aware of. We had a question over here.
Does it matter whether your existing water supply, hot water system is mains pressure or it's from tank in the roof and low pressure?
It doesn't because the heat pump has its own circulating pump. So we can just circulate out of that gravity fed tank model and then back in again. So it doesn't have to be mains pressure at all. The heat pump is still doing the job. The problem is though with the gravity fed tanks, they're very, very small usually. So you don't have a lot of storage capacity.
Okay, that's really the key with a heat pump. I mean, the difference between that and, say, an electric element or a gas burner, those two energy sources got a lot of energy in a very quick time. So they can heat up, quickly. With a heat pump, it's putting a small amount of energy in by comparison, like about 3.5 kilowatts of energy in. So it needs a bit of time to do the job. That's what it does need. And then you really need to store it. So we would say, I mean, you can put the heat pump to a tank of that size, but really to get value out of it, I would say the next size up, the 250 litre or the 315 litre would be better.
Excuse me, well, I have to go because I've got another engagement, so my apologies, but I'm sure, Dave will be able to answer all your questions.
Thank you.
And thanks very much for listening.
Okay, we had a question here and then over there.
If you're intent on running a heat pump off a solar PV system, how much extra capacity should you add to the PV system to compensate for to allow for the demand of the...
We did some modelling in the buildings plan for that. You go first and then I'll...
Yeah, have a go. Yeah, people ask that question a lot. I say my standard answer to that is a 1 kilowatt PV system will do the job of that heat pump. Basically, it's going to use 1 kilowatt per hour. So if you say on average there's 4 daylight and sunshine hours in a city like Melbourne, then we've got 4 kilowatt hours. So we need 3 of them. So that's about what we would need. I'd say a 1 kilowatt system would do the job. What's your answer?
Yeah, that agrees with our analysis. We concluded that if a house extended the solar array that it's probably already going to get by an extra kilowatt of capacity, then over the course of a year, the extra generation from that kilowatt of capacity would balance out the heat, the electricity needs from the heat pump system for a typical home. Which is another argument in favour of heat pumps against solar hot water, because having one array on your roof instead of PV plus solar makes a lot of sense.
So you could run it in conjunction with the timer, the 24-hour timer that determines when is the most optimum time to run the heat pump.
Control is another big question that isn't adequately addressed by current products in the market. But if you just look at it from a net energy argument, it makes sense regardless. Are we here?
Yeah, I was really going to ask the same question. What are the electrical requirements for running that heat pump?
Yeah, what do you need? Okay, they draw between 3 and 6 amps. So at the beginning of the heating cycle, they're drawing about 3 amps. Toward the end, as they push up to 60 degrees, they work a bit hard. It's like just sort of going steadily up a hill. And they're drawing about 6 amps, or just over that, by the time they kick out. So we would say to people, ideally we'd say a dedicated 15 amp circuit is what we like, but if you've got a dedicated 10 amp circuit, that'll work just fine. We have a problem if you had a 10 amp outlet and you hung a whole lot of other things off that circuit back to the switchboard, well then you probably force the breaker to trigger those other things to kick on at the same time.
Yeah, I think there's another answer to that as well, that the current electrical code requires that an electrically driven hot water service requires a 15 amp circuit regardless. And that, from my perspective, that doesn't make sense because you probably don't need 15 amps if you've got a heat pump. But on the other hand, you can't be assured that if that unit fails, that the next owner of the house isn't going to replace it with something that needs a higher current. So, yeah, so an electrician will probably put in a dedicated 15 amp circuit, even though it doesn't need it.
Yeah.
Vivian?
Thank you. Where do you buy them? And how do you find a good installer? Because when we saw the photos of the poor installation, and the gentleman here said, well, the electricians, I've also met plumbers and electricians who don't seem to feel the same way about sustainability at all.
No. Look, in terms of where you buy them,
what was the question?
Dave and Earthworker, I suppose, have got on...
The question was, where do you get them?
Our website, and we've done a partnership with Laser Plumbing.
Can you get them all over Australia?
Yes,
Or just Melbourne?
we'll push them out through Australia. In fact, we're hoping to get into this agreement at Port Botany, the maintenance workers. There's 680 of them, so we'll be sending them new south.
So we have preferred installers around the country. Laser Plumbing is an example of that. But the thing about this this heat pump, if you were in some location where we couldn't get one of our preferred suppliers, and there's only one plumber in town. We sold one to Bremer Bay last week. Bremer Bay is in Esperance. There's a little community that couldn't be more remote if you try. And so, they don't have a lot of technicians in town. So, you just use the local one. The thing about that bolt-on is it's been designed with all of the heat exchanging and everything within it. So it's like purchasing a little bar fridge or something, really. Just plug it in, find a spot for the sensor truck can fly the turn lines up, and it will go. So it's not a lot to get wrong. We try to make it really, dare I say idiot-proof, but, simple to connect. And so most plumbers, even a plumber who's never seen one before, would be able to make it. I think could install it. But having said that, as Dave said, we do have preferred plumbers who've seen them before, done the installation, and they can do it much more.
Can I just say too, we're going to do direct supply to the plumbers so that they won't have to go to TradeLink or Vize or anyone. We'll courier it out to the job, at least in Victoria initially. And also the PCAC, the Plumbing Industry Climate Action Centre there in Brunswick, they're going to do an earthworker accreditation so that, the plumbers we would always preference first would be the ones who do that short course.
Right at the back and then in the glasses.
Yeah, a question about the timing that was briefly mentioned. Is it possible to just run this on off-peak, or should it run during the day?
Yeah, no, that's a very good question. We get that question a lot also. So the answer I make to that is that heat pump will run between -5 degrees and 45 degrees. But at 7 degrees is where it gets clear of its de-icing, its need or its requirement to go into a defrost mode from 7 degrees up. So when it goes into defrost mode or de-icing, it actually runs backwards for about 2 or 3 minutes, and it just goes forward again. It's like running off sand, you step forward a little bit back. Above 7 degrees, it just goes straight up. Now, to answer that question then, you have to ask yourself, what's the temperature difference between the night time and the daytime? Now, in a city like Melbourne, it's about 10 degrees on average over the whole year. So if you run it at night and you get your nice cheap tariff, that's good. But you are going to run it, because it's 10 degrees cooler, it will run for 20% longer. So you're going to gain maybe a 45, let's say 50% discount. So you're going to have to add on 20% for longer run time. So it's a swing and a roundabout. So the afternoon is the best time to run it because it's warmest and it will run best. And I would say to people who live in, say, somewhere like Woodend, because the winters are really cold, or some parts around Victoria like that, I would say to them, look, if it were me, I would be putting on a continuous tariff and running it during the afternoon. Or you get a smart meter, when you run it in that little window you've got, it'll be off before the peak comes on. That would be ideal for it.
I actually do use it when it's
No, I don't think there was a
feed-in tariff for the solar system that we've got on the roof. So for me, the difference between off-peak and what I get for feed-in tariff.
So then what we say to people is that the unit has a time built into it. So we say, right, you set the clock and you set the timer. Now, if you're trying to work your PV out and you want it to feed in, you don't want it to be drawing power while it's feeding. If that's what your driver is, well then you set the timer and bring it on, say 4 p.m.
Yes.
Still plenty of warmth in the air, and then let it run and let it run up till say 7 is probably when it would need to run, and then turn itself off.
Okay, thank you.
Yeah.
Just a question, what's the cost of these bulb?
Well, I can quote you the recommended retail price, and then you go and find someone's arms to twist and see what sort of a deal you can do. But the recommended retail price is $1,890, including GST. That's for the bolt-on unit. If you team it up with the 10, you'll wind up with the recommended retail price with the 315 litre version of that. So it's one that stands about twice as tall. It's that, $3,690 including GST. Now, government rebates at the moment are about $1,000, so it takes it down to $2,690. So, you're starting to get a price that, if you're going to save about $600 a year in your running costs, your typical family of 4, well, you're starting to look around sort of 2 to 3 year payback. And that's kind of the sums that people have to make their mind on.
Low income families, we've done a partnership with Miku, cooperative bank, and they've knocked off over a percentage on their normal green line for workers. So, with a 5-year fixed term, that's subject to some variation depending on conditions for them. But that's a good deal, and low income families can afford it.
What is your website name?
That's earthworkercooperative.com.au.
Okay.
So, just 2 more questions. There and there.
When you're talking about cost savings, are you comparing that with the mains electricity?
Yes. I should have said that. That's the standard comparison we use. Is mains is electric element water. We use that as a comparison.
What's the comparison with gas? Broad figure?
It's still actually cheaper. I think it'll cost you about. I could be, in my head, I'm thinking about $350 a year to run that on mains. So the bolt-ons about $200 a year to run it. Electric element about $800. But if you've got a gas bottle off the grid, and unfortunately there's one hell of a lot of those around, and I don't understand at all why they even get out there. But they're usually talking maybe $1,200 or more to run there.
Okay, last question here.
Have you got a figure on the heat loss in the tank, so to say, 12-hour period?
Yeah, no, what we quote is over a 24-hour period, it's generally about 1.5 to 2 degrees heat loss is what you lose. So when people say if the thing runs between 12 and 3 or 12, something like that in the afternoon, and then I have bath at night and I had a shower in the morning, I'd say yes you can, because there's still be a lot. That's like a big thermos, it really is, and it holds the heat very well.
Can I just make a comment on that? The modelling we did for the buildings plan on hot water services showed pretty clearly that the smallest storage unit you can tolerate is going to give you by far the best performance.
Yeah.
So choose the smallest unit that's not going to let you run out of hot water during the day, and that will have the lowest losses over the course of the year.
A two-part question. I was going to say they're not got 6 kV of solar on the roof. Would I be best to buy one of these units, charge it up during the day when the sun's shining, and not use off-peak electricity at night? Would I be ahead, do you think?
Depends on your feed-in tariff.
Sorry.
Depends on your feeding
Oh,
tariff.
well, you're only using part of the feeding tariff and get 8 cents for it now, so it's pathetic anyway.
Okay. So if you're only earning an 8 cent feeding tariff, then avoid, get as much self-consumption as you can.
No, that's. I think it's that part of the feeding tariff that's driving the move towards people going off grid.
Oh, next house we offer
You know, there's a whole. Yeah, I was on the ATA stand at Jeff Shed on Friday, and they've got their latest magazines all about going off grid. So it's that kind of thing that's driving it.
I'm afraid we're going to have to call it quits there. We're running out of time. The coach is going to turn into a pumpkin shortly. I'd just like to say that BZD is run by volunteer donations from the public. BZD is not affiliated with any political or business, so we rely on contributions from just ordinary people like you and me. So if anyone's interested in contributing to BZD's work, we'd be very happy to talk to you. There's sort of big some forms outside on the table to fill out if you'd like to do that. There are probably quite a few more questions here, and we'd like to invite everyone to come to continue tonight's discussion over drinks next door at the Clyde. The kitchen's open until 8:30 if you'd like a meal. Are you gentlemen able to do that? Yeah. You can't? Okay. Chris can?
Yeah.
Dave can't? Richard?
Yeah.
Richard can? So if anyone would like to ask some more questions, pop around the corner to the Clyde. Outside the door there we've got some DVDs of past discussion groups, if anyone would like to go back over past discussion groups for a gold quality donation. And our next discussion group is on Monday the 4th of August, and at long last we've got David Caroli as the speaker, and the location is here. And that's it for me. Thank you all for coming, what a great turnout.